Chemical bonding. Shapes of molecules and the valence shell electron pair repulsion theory. Essential idea we'll be looking at. Lewis structures show the electron domains in the valence shell and are used to predict molecular shape. We'll also look at larger structures and more in-depth explanations of bonding systems and how they often require more sophisticated concepts and theories of bonding. The natures of science we'll look at. Science again, they use models to represent the real world, and we'll look at the valence shell electron pair repulsion theory here, and also we'll want to think about the principle of Occam's razor. And the bonding theories have been modified over time, and the new theories need to remain as simple as possible whilst maximising explanatory power. For example, the idea of formal charge. Okay. The shape of a small covalent molecule is determined by the position of its nuclei. Here you can see a model of carbon monoxide. The black sphere is carbon, the red spheres are oxygen. And you can see it's linear, it's straight. The grey links in the models represent the shared electron pairs, but the shape of the links don't truly reflect the actual position of electrons, so we don't consider them when we look at the shape of the molecule. This is a model of what is really going on. Representing it is the Lewis dot diagram. Some basic shapes of molecules and polyatomic ions. You can see here we have a model of water, hydrogen in white, oxygen in red. You can see it's kind of angular, it's a bent, it's a V shape. Oops. When we draw the Lewis dot diagram, we draw it straight, it looks linear. Model of methanol. Then we could call it trigonal planar. Trigonal, there's 1, 2, 3 atoms, and they're all in the same plane. However, if we were to draw a Lewis dot diagram of this thing, of methanol, then it looks like a upside down T. It's a T shape. If we were to make a model of ammonia, then you can see it is a trigonal pyramidal structure. Trigonal because there's 3, and it looks like a pyramid. If we were to draw it, Lewis dot, again it looks like a T shape. Here we have methane, and it's tetrahedral. If we draw it out with Lewis dot, it is a cross shape. The Lewis structure is a 2D representation. It doesn't accurately show the 3D shape of a molecule. For example, the Lewis structure suggests a linear shape for water. The actual shape is a V shape. It's a bent shape. However, if you know the Lewis structure, you can deduce the shape of the molecule. It's all about how electron pairs are arranged around the central atom. A theory that lets you predict the shape of small molecules is VSEPR, valence shell electron pair repulsion. The basic premise is the electron pairs in the valence shell will repel each other so that they are as far apart as possible. We will focus on what happens around the central atom of a molecule. If you know how many electron pairs are arranged around the central atom and what type of electron pairs you have, then you can predict the shape of a molecule. The electron pairs that repel each other as far as possible in the VSEPR theory are a bit different than what we see in a Lewis structure. So, one valence shell electron pair repulsion electron pair could be either a lone or non-bonding electron pair, LEP, lone electron pair, or the one bonding electron pair bonding electron pair in a single bond, the 2 bonding electron pairs in a double bond, and the 3 bonding electron pairs in a triple bond. We're going to use the term electron domains for these valence shell electron pair repulsion electron pairs. And I'm going to say electron domains in a low voice to help remind you. Electron domains. Splendid. Determine the number of electron domains around the central atom here. Well, here we have 4 electron domains. Bonding, bonding, non-bonding, non-bonding. Here we have 2. A double bond, a double bond. Here we have 3. A double bond, a single and a single. Here 4. Single bond, single bond, single bond, lone pair. And here 1, 2, 3, 4 single bonds. So 4 electron domains. There are 5 basic arrangements of electron domains around an atom. When there's 2 electron domains, the electron domain geometry is linear. When there are 3, the electron domain geometry trigonal planar. 4 electron domains gives us tetrahedral. 5, which is HL only, gives us trigonal bipyramidal, and 6 electron domains gives us octahedral. Note the HL only. Here's an example. The number of electron domains around the central atom is 3. There's a double bond, a single and a single, 3. The bond angle is 120. The electron domain geometry is trigonal planar. The molecular geometry is also trigonal planar. Now, I bet you're wondering why I've written this twice. And you'll see that this makes good sense in time. This angle here is 120, as is this one. Okay, let's look at this one. We've got carbon dioxide. We've got 2 electron domains, 2 double bonds. The bond angle is evidently 180. The electron domain geometry, linear. Obviously you can see that it's nice and straight. And molecular geometry, also linear. I'm writing the same thing again here. What's going on? Okay. When there's 2 electron domains, for example carbon dioxide, the bond angle, the electron domain geometry and molecular geometry is as follows. Linear, linear, and 180. 3 electron domains with no lone pairs. An example would be methanol. The electron domain geometry, molecular geometry, and bond angle are as follows. Trigonal planar, and we have a bond angle of 120. Things are going to change a bit here, and you'll see why I was writing things twice. There's 3 electron domains, and 1 is a lone electron pair. You can see the lone electron pair here. 2 oxygens in sulfur dioxide. The lone electron pair does not contribute to the shape. Okay? Only the nuclei do. So, lone electron pairs occupy more space. This occupies more space than the bonding electron pairs, and this pushes the other electron pairs closer together, reduces the angle. So this angle here would be reduced. The electron domain geometry is clearly trigonal planar because there's electron domain here, electron domain here, and electron domain here. But the molecular geometry is bent or angular because we don't include the electron pair. We only include the atoms, and so it's bent or angular. And the bond angle has gone down from what we expected. When this was an atom, if it was an atom, you'd have 120. But because it's a lone pair, it's pushing this electron pair and this electron pair together here, giving us 117. Let's look at a molecule with 4 electron domains and no electron pairs. Methane, for example. The electron domain geometry and the molecular geometry both tetrahedral. When there's no electron pairs, these are the same. And the bond angle is 109.5. So this bond angle here, 109.5. Now 4 electron domains with 1 lone electron pair. You can see the electron pair up here in ammonia. The lone electron pair doesn't contribute to the shape, only the nuclei do, remember that? And the lone electron pair occupies more space, so it's going to be pushing at these bonding electron pairs. It's going to reduce the bond angle. Here. The electron domain geometry is tetrahedral because you include the lone pair. The molecular shape, we don't include the lone pair, and so you can see it is trigonal, pyramidal. And the bond angle is 1,7. It's less than what we would expect because this lone pair is repelling these bonding electron pairs. Okay, what if we had 4 electron domains and 2 lone electron pairs? And we have this in water. We've got the 2 electron pairs at the top here, and we've got hydrogen and hydrogen with the oxygen in the middle there. The lone electron pairs don't contribute to the shape, only nuclei do. The lone electron pairs occupy more space and they will push against the bonding electron pairs. So the bond angle, the electron domain geometry and molecular geometry are as follows. It's tetrahedral, because we include the lone pairs. The molecular geometry, bent angular, we don't include the lone pairs for molecular geometry. Oh, there's that wind again, the typhoon. The bond angle is 104.5. It's reduced because of these electron pairs which occupy more space. So, HL only, 5 electron domains with no lone electron pairs. We know the electron domain geometry and molecular geometry will be the same, and it's trigonal bipyramidal. The bond angle is 90 and 120. 90 here, and 120 would be like around there. Can't see that too well, but I'm sure you get the idea. Okay, 5 electron domains with 1 lone electron pair. We've got the 1 lone electron pair up here. We know the electron pair doesn't contribute to the shape. So, the electron domain geometry is trigonal bipyramidal. Trigonal bipyramidal. You've got the straight part there, and you've got the trigonal part there. Molecular geometry is a seesaw, and you can imagine this would be the seesaw there. That would be the central part. We're not including the electron pair in the molecular geometry. And the bond angle, 90, 117 and 180. We have 90 between this and this, there, okay. We have 117 between these two, and the 180 is from there to there. Right, 5 electron domains with 2 lone electron pairs. Here they are at the top. They don't contribute to the shape. So the bond angle, electron domain geometry, molecular geometry. Electron domain geometry, when we include the lone pairs, is, again, it is trigonal bipyramidal. The molecular geometry is T-shaped, so let's forget about those lone pairs. And you can see it's a nice T. And the bond angle is 90 degrees and 180 degrees. 90 degrees be there, and 180 degrees between those two. Five electron domains with 3 lone electron pairs. So there's 3 lone electron pairs here in xenon or xenon difluoride. The lone electron pairs aren't going to contribute to the shape. The bond angle, electron domain geometry and molecular geometry are trigonal bipyramidal. There we go. There's the trigonal part. That would be the top of the pyramid, or this is the other top of the pyramid. It's linear if you don't include those lone pairs. So the molecular geometry, straight. And the bond angle is 180. And it's obviously between the two fluorine atoms. Electron domains with no lone electron pairs. We've got octahedral electron domain geometry, octahedral molecular geometry, and a bond angle of 90 degrees. There's sulfur hexafluoride. 6 electron domains with 1 lone pair. The lone pair is drawn in at the bottom this time, just to shake things up. The lone electron pair does not contribute to the shape, as we know. The electron domain geometry is octahedral, or including the lone pair. The molecular geometry is square pyramidal. It has a square base. And there's the top of the pyramid. I'm just going to draw in the full pyramid for you. It's quite exciting. There we go. Square pyramidal. And the bond angle is 90. So from there to there, 90 degrees. Six electron domain and 2 lone electron pairs. We've got the lone electron pairs on the top, on the bottom here. The lone electron pairs don't contribute to the shape, bond angle, etc. The electron domain geometry is octahedral, including the 2 lone pairs. The molecular geometry is square planar. It's flat. Okay, not including those lone pairs. The bond angle is 90. And I guess if you wanted to include, we wouldn't include that one. That one there would be 180. Not 180 degrees Celsius. I don't know why I drew. Don't know why I wrote Celsius. Let's move to the next slide. Here is a table, and it kind of brings everything together. The number of electron domains down here. It gives you the electron domain geometry here. It shows you the number of lone pairs. It gives you the molecular geometry, and it doesn't give you the bond angles, but it does now. You do need to know this information, and you can see there's kind of a pattern to it. In linear, you have no lone pairs, trigonal planar, 0 and 1, tetrahedral, 0, 1, 2, trigonal bipyramidal, 0, 1, 2, 3, and octahedral will go back down to 2. So you've got, like, it goes up to 1, then 2, then 3, and back down to 2. And the molecular geometry, when there's 0 lone pairs, is always the same. So for electron domain 3, it's a trigonal planar, tetrahedral, molecular geometry, tetrahedral, trigonal bipyramidal, etc. So there's not as much for you to remember as you think. Some of the angles are obvious: 180, 120, 109.5. You'll just get accustomed to that one. But you do want to kind of remember the ones where things have changed, such as 117, 104.5, and 107 there. Okay. Please go to these sites to view and manipulate the molecular models. It'll give you a very good idea of the geometry. All of the images in this came straight from Wikipedia. Goodbye.